Chapter 19, we started to look at this sort of stuff in concept of circuits. In chapter 19, we didn't draw circuit diagrams yet. That was chapter 20. Chapter 19, we started with current. Andrew, what's the symbol for current?
I, which is amps.
Okay, we'll go with amps. We know the dimensions for it are amps.
Sorry.
That's okay. And capital or lowercase?
Capital.
Capital. Carlone, the equation for current?
The change in charge over in time.
Change in charge over change in time. Literally, it is, if you were to count the charges as they go by and divide by how long it took for that amount of charge to go by, you would have the current. And it is in amps. And an amp, Mr. Smith, is what?
Coulombs per second.
It is charge per unit time, or coulombs per second, and amps are a base SI unit. We now that we have electric or currents, we can talk about electric potential difference in terms of current. What is the equation that relates electric potential difference and current, please? Current. We have electric potential difference and current now. What is the equation that relates them?
The electric difference equals current times resistance.
We now have this concept of resistance, the symbol for which is a capital R. What are the dimensions for resistance, learner?
Ohms.
Ohms. Hedler, how do you spell ohm?
OHM.
OHM. Ohms. What is the symbol we use for ohms? Capital omega. How do I draw a capital omega?
Oh, wait.
Riku.
Oh, I'm saying that one too.
It isn't. How do we know what's upside down?
Well, let's just say everything's falls out.
What falls out?
A lot.
The light.
Whatever.
Or whatever. Very nice. The upside down horseshoe. What is an ohm? Please. Well,
Volts per amp.
it is a volt per amp. If you rearrange this equation, you're going to get resistance equals the electric potential difference divided by current, or volts per amp. Electric power. We have a bunch of three, to be exact, equations for power. Danaher, please give me all three equations for power.
Okay. Current times potential difference. Current squared times resistance. And potential difference squared over resistance.
Three equations for electric potential energy, or electric potential power. Electric power, excuse me. All depends on what you have: current, electric potential difference, or resistance. What are the dimensions for electric power? Christine. Watts. What is a watt? Wicked. Joules per second. It is the rate at which we are converting electric potential energy into some sort of other form of energy: heat, light, or sound. That is chapter 19. Chapter 20 was taking that and applying it specifically to circuits. So we had to draw circuits. For example, I could have a short line and a long line and some wires here. This short line and the long line represent what? Flo? This symbol.
Oh, it's a battery.
It's a battery. Okay. What am I going to put next to this battery to identify it? What are the symbols I'm going to put next to the battery? Hannah? Yes, I'm going to put a plus or minus. Absolutely. Where do I put the plus and the minus? For example, I have the short one on the top here. Am I going to put a negative or a positive on that one? Kosa?
Negative.
This is the negative terminal. The top one is the negative terminal. The bottom one is the positive terminal. I still need a symbol next to it to identify what it is. I'm going to put on there, learner.
Change in V, which is the
Close. I need a subscript.
T.
sub T. The T stands for Wicket. Terminal. This is the electric potential difference or the terminal voltage. I can put this in a circuit with something that looks like this, or at least remotely like that. What is this item, Carlo?
It's a resistor.
It's a resistor. I can also put this item in there. This would be what, Duval?
An open switch.
This would be an open switch, which would make this what type of circuit, Lily? This is an open circuit. Now, I know this question is confusing. If I were to close the switch, what type of circuit would this be? Wicket? I know. It's a confusing question. It would be a closed circuit. If I were to take a positive anthropomorphic charge and to place it right here on the wire and ask that question, that anthropomorphic charge, which direction do you feel compelled to move? Which direction would that charge move? Charlotte? That way, to the left. Note comes back to the law of charges, which we have correctly written up here. The positive charge is going to be attracted to the negative terminal and repelled away from the positive terminal. Therefore, it would feel compelled to move that way. So if we close the switch, we're going to get current is going to flow from your vantage point counterclockwise. We have another type of circuit as opposed to an open or a closed circuit. What was the third type of circuit we talked about? Cosine.
A short circuit.
A short circuit. What is a short? What is a short circuit? A short circuit. Sims. It's a very low resistance circuit. It's not designed to have that low resistance. It's a circuit that's designed to have a normal resistance. Then suddenly, for some reason, that resistance is decreased quite a bit. We try to avoid creating short circuits where you are the low resistance piece. Oh, let's see. Yeah. Okay. So now we can create a circuit with two resistors. So we'll have the terminal voltage resistor 1 and resistor 2. These are two resistors in rubber. What?
Series.
These are two resistors in series. Looking at this, we know they're in series because our anthropomorphic charge will go through both resistors. So the resistors will be in series. When you have two resistors in series, the equation for the equivalent resistance then, Christina, is what? Bless you. When you have two resistors in series, I'm looking for the equation for the equivalent, bless you, resistance. Looks like Christina could use some help. Who wants to help her out? Wicked.
Resistor 1 plus resistor 2.
When we just have two, it would be resistor 1 plus resistor 2. Assuming we have more, it's just going to continue to add them. When you have resistors in series, the resistances simply add. We know stuff about the currents and the electric potential differences when you have resistors in series. Pooja, give me one or the other. What do we know about either the current or the electric potential difference?
Total current is equal to all current and
Like so? Sims? All the currents are equal. Remember, when they're in series, our anthropomorphic charge has to go through resistor 1. It also has to go through resistor 2, also has to go through the battery. So they're all going to be equal because you're going to have an equal number of charges go through each one in the same amount of time. So those currents are equal. What do we know about the electric potential difference for resistors in series? Electric potential difference.
The terminal voltage is equal to the electric potential difference for resistor 1 and plus the electric potential difference of resistor 2.
Great. We have two resistors in series. Okay, we can also have two resistors, if I draw them like this. This would be 2 resistors in what, Miller? Christina, help him out. These are 2 resistors in. Mr. Smith, you're caught in the middle there.
Parallel.
In parallel. 2 resistors in parallel. When we have resistors in parallel, we know the equation for the equivalent resistance for 2 resistors in parallel. Miss Song, what is that equation?
1 over the inverse of 1 over resistor 1 plus.
I'm going to stop you for a second. The inverse of 1 over resistor 1 would just be resistor 1. So this is just the inverse of resistor 1 or 1 over resistor 1. Right?
Oh, right, okay. So the inverse of resistor 1 plus resistor 2.
I'm sorry. The inverse of resistor 1 plus
The inverse of resistor 2.
plus however many we have.
And then inverse.
The inverse of this. The inverse of the sum of the inverses of the resistances. We know stuff about the currents and the electric potential difference for 2 resistors in parallel. Hannah, tell me one or the other, something we know about either electric potential difference or current. The terminal or the total current is equal to? The currents are going to add because the charges have to split between resistor 1 and resistor 2. Good. And the electric potential difference, Dana? Great. When they are in parallel, all the electric potential differences are the same. So let's just take a look at a circuit, because part of the issue with chapter 20 was being able to look at a circuit and to figure out the equivalent resistance and the power dissipated in a circuit resistor, things like that. So let's start with a battery. Then we're going to have a resistor, a resistor, a resistor, a resistor, a resistor, a resistor, a resistor. This is fun. Another one. And then we're going to connect this back to. So we have our terminal voltage. We have resistor 1, resistor 2, resistor 3, resistor 4, resistor 5, resistor 6. This is going to be resistor 7 and resistor 8. Oh, I'm sorry, I missed one. Resistor 9. Okay, I feel better. We're not going to go through and solve this, but we're going to talk about how we would solve it. Basically, what you need to do is you need to look at it and be able to identify resistors that are in series or parallel, and then start combining them to create equivalent resistors, and then redraw the circuits and all that. We went through this several times. Let's just talk our way through it a little bit. Look at this and tell me what you see as far as 2 resistors or 3 resistors that are in blank. Headley.
Resistor 1, resistor 4 in series.
In series. Resistors 1 and resistor 4 are in series. Therefore, we can add the 2 resistances together to get an equivalent resistor 1, 4. Andrew.
Resistor 3 and resistor 7 are also in series.
Also in series, so we could get an equivalent resistor 3, 7. Now that we have equivalent resistor 1, 4 and equivalent resistor 3, 7, what do we know about those two? Kosa.
Well, 1,4 is parallel with 3,7.
Right, the equivalent resistance 1, 4 is in parallel with equivalent resistance 3, 7. So we can figure out a total equivalent resistance for this piece. What about this block right here, 5, 2, 6, and 9? What do we see there? Wicked.
Resistor 5, 2, and 6 are in
5, 2, and 6 are in series because a single charge will go through all 3. Therefore, we can figure out the equivalent resistance of 5, 2, 6. Now that we have equivalent resistance 5, 2, 6, what do we know about that versus resistor 9? Emily? They're in parallel. So 5, 2, 6 is in parallel with 9. We can figure out an equivalent resistance now that we have the equivalent resistance for 1, 4, 3, 7 and 5, 2, 6, 9. How do those compare to a resistor 8 here? Danaher?
The two blocks are both in series with resistor 8.
It's a great way to say it. 1, 4, 3, 7, 8, and 5, 2, 6, 9 are all in series. We could then figure out equivalent resistance, and we've gone through and done examples just like that. Great.